Hello, and welcome back to another lecture of AI for Retail Executives. In this course, this is a very exciting course. You are going to train your first deep learning model. You're going to say, Francois, there's no chance you're going to get me to do this. I'm telling you, you're going to be able to do it, and it's going to be really, really cool. Okay, so at this point, we expect that you've taken the AI basics lecture, and you've taken the optimization lecture. So by this point, you should understand what a loss function is, what cross entropy is, what stochastic gradient descent is, and all these different terms. And so we'll talk about it a little bit in here, but we'll presume, I would recommend you go back to those lectures if you haven't watched those yet, so that you come in here ready to rock and roll. All right, so what I want you to do is pull up playground.tensorflow.org. You just plug that right into your browser, and you're going to get this UI. And this is what's called a WYSIWYG, or what you see is what you get. And it is a very cool tool to help you break apart the AI training process, the deep learning training process of a neural network, and make your own architectures, train your own models, and, optimize your hyperparameters, all that kind of stuff. And so I'm going to explain every single part of this dashboard so that you understand what's going on. So the first thing we're going to do is we're going to pick classification. I think classification is better for this example. And you can see that there's all these different types of data problems that we can go and solve. We're going to solve this one at first because it's the easiest. And what we're looking at here is, let's say this is the x-axis and the y-axis. We can give a real example, so there's something there. Let's say that the x-axis is the standard deviation in price of the house, and the y-axis is the standard deviation in the square footage of the house. Okay, and so right here would be the median house price. Right here would be the median, median house price along this axis right here, right, this line. And then right here, let's say, is the median square footage of a house. And then you can see there's kind of these two clusters. And let's say that those two clusters are two different cities. And if I give you the house price and the square footage of the house, I want you to predict which city it is. And let's say that, this is Seattle and this is Washington, D.C. Okay? And so now I'm going to give you only the X's, and I want you to predict, Boolean, is this in Seattle or Washington, D.C.? Okay? So that's an example task. So we have these two nice clusters, and let's make it a little bit harder. So we're going to increase the noise of this data set to be a little bit more difficult, because the real world is a little dirtier than that. Actually, let's leave it there for now, just so you can see kind of what's going on. And so we're going to train our deep learning model. We're going to make a really simple one, a 2-layer model, and we're going to have 2 neurons. And I'm going to explain the math here in a second, but let's get to the fun part of actually going to make the magic happen. And let's just default stuff. Let's just let it learn and say, oh, very cool. So look, it learned this decision boundary right here, which clearly linearly separates the linear, because there is a linear decision boundary here. And it finds this perfect example separating the two clusters. And so now we'll show the test data and see what it and discretize it. And so you can see that we got 100% test accuracy. Amazing. It was a very easy example, so we shouldn't feel too proud of ourselves here. So what we're going to do is make it a little bit harder, and let's see if that's still possible. And we're going to retrain again. And you can see here the test, the data is a little noisier as per the real world, and it has kind of like this little S kind of thing. So it's not so much a line as much anymore. And you can see the test data here. We're not at perfect accuracy, so training loss and test loss isn't 0 like it was in the previous example, but it did pretty good. So now that we got there, let's back up and see what the heck is even happening here. So remember I told you about SGD. We'll go back to our whiteboard here. And we start off with some initial theta, 0, and we're going to say it's going to be, 0.5, 0.5. And we don't know. It was something like that. And then we're going to put that into our model, and we're going to have some h theta that's going to take in as input our x1 and x2. And then we're going to use that to make a prediction for y hat, which that is output of softmax, but you don't need to know all that stuff. And then we're going to have our truth label y. And we're going to compare the two with loss. And we talked about cross entropy loss. And so this is cross entropy loss. You don't really need to know too much about that. But now that this outputs some amount of loss. And so you can see here, when you go here, you can see this loss thing. That's what it's outputting, is the cross entropy loss. And so, and it tries this, it gets error, and then this is my error. And then I back propagate that to, so I go back here. So I get my H theta, I predict y hat, I compare it to y via cross entropy, and then I get some error. And then now I back propagate that error back into my theta, and I get theta 1. And that's going to be theta 0 plus lambda, minus lambda, doesn't matter, of cross entropy of y hat and y. And I update my theta. And then I try it again. And I just keep doing that. And then I go back to here, call this 1. I get a different y hat here. I get another y hat here. And then I get another cross entropy here. I get more error. I back propagate that right through there, my error, to update my thetas again. And then I go back around. And that's basically what's happening until my loss, effectively, until this term right here hits 0. And so once it's 0, there's nothing else to learn. The derivative of my loss function is 0. There's nowhere to move, no better to optimize. And so you can see that here. You can see that the loss function basically hits 0, and that's all you can do. And so, so now let's make this a little bit more challenging. Let's say it's something like this, and we'll give a really, really small model, and I'll explain the math of what the model is doing, of what our H theta is in this example. But in this example, you'll see we have a very small model. We only have 2 neurons, and that's all we can do. We cannot get more accurate because we don't have a high enough capacity model. And so we'll try this again, but we're going to see that we just do not have enough capacity. So what we need to do is add capacity. We need to increase the number of layers and increase the number of neurons per layer. And so once we do this, let's see what we learn. Looks pretty good. It's finding a decision boundary that's right in the middle, right in the target there. So this is exactly what we want to achieve. So all that's good. And we can make this noisier if we really want and see if it would still learn. But it's all going to learn fine. And so remember, one thing that I want you to play around with is batch size. And so when we are performing stochastic gradient descent, the S in stochastic gradient descent, what makes it stochastic is that we're not taking per every single loop in our training loop, we're not taking all of the data. We're only taking a very small subset called a mini batch. And so batch size is how many of these examples do we want to pull in. There's pros and cons to having high and low batch size. A high batch size is fantastic because you know that your gradient direction is in the right direction. It's bad because the compute is very high, so your model's going to train very slowly. And so when you're doing this, there's kind of a perfect sweet spot of what's too big, what's too small, and you kind of have to find that. And generally for machine learning, 32 is a common number, things like that. And so so that's all that part. And so you can see kind of what happens. Let's say that if we put a batch size of 2, and we're going to train. Let's see if this trains slower or faster. And so you can see that we got through iterations quickly, but it was kind of diverging a little bit, and then it came back. And if we make the batch size very, very big, it's going to take a little bit more while to train, but when it does, it's very stable. And you can see that every step in the gradient every step is very strong. And so you can see it's very smooth training, it's very reliable training, but it takes a while, and we got stuff to do. All right, so now let's get you can look at this example too. I think this is a pretty easy kind of one. I don't think this is as complicated of a different, we can actually play around with that one. And what I want you to do is try to solve this one. So let's bring your noise to very small. This is a very classic, this is a spiral data set, is notorious as a very, very difficult model to, or a problem to solve. And so if your data looked like that, you can see how difficult it would be for your machine learning model, for your deep learning model, to try to predict this stuff. So I want to explain, before we give this problem, what I want to do is explain the math that's kind of happening here. And so you have these two scalars, two numbers, 5 and 6. And then these numbers are getting put into each one of these neurons, multiplied by some weight. And so you take 2 times this weight, which is 0.6. We'll call that theta. This is one of the thetas, and it's coming in here. And then this is an activation. So this is a neuron that's being fired, and it's producing this map. And same thing here. So you take this number, which is 3, let's say, you'll multiply it by negative 0.8 to produce 3 times negative 0.8, whatever that is, and that goes right there. And then what you're going to do is, now you have these, let's go back to here. So you have your x1 and your x2. Let's call this x right there. And then I'm going to have my first layer, which will be, I'll call it theta 1. So I'll have x theta 1, transpose x theta 1, to output my activations. Let's do it like this, actually. I have, it's easier if you just do this. x1 theta 1, x2 theta 2, x1 theta 2, x2 theta 1. Okay? And so that's basically what you're seeing here. So you start out with x1, x2, like that. And then this is going to get summed up. So we have theta 1 is my neuron here. And I'm going to sum up those values, and I'm going to threshold it. If it's a negative value, I drop it to 0. If it's a positive value, I keep it. And that's called a rectified linear unit, or ReLU. And I'm keeping only the positive component. That introduces nonlinearity. The nonlinearity is very important. If you didn't have that, the thing wouldn't train. And so that's very, very important. And then I sum up these two here. I do the same thing, and that's my activation here. And then rinse, wash, repeat. And I do this. This is one example of every single layer. And so that's what I'm doing. And then when I get to the very end, then I have a softmax. So I'll just explain that function a little bit. It's kind of, too much detail probably, but I'll come out with some activation 1. That's not an A. Some activation 1, activation 2 for the 2 classes that could possibly be. And these don't sum to 1 yet. And so I'll put it, you can look up the function, but just for simplicity, I put it through a softmax function or a sigmoid, and then it comes out to be probability of 1, probability class 2, and these do sum up to 1. And so, I'm not showing my screen, just like that. And then those go into my cross entropy model, my negative log likelihood, whatever you want to call it. And this, we'll treat this one, this P as my y hat. It doesn't really matter. You can treat either one. And so that's my y hat, and that goes in here, and y. So, and you can think about every single layer as as like a bunch of these polygons that I can fit. And so, meaning that I can have, since I'm basically doing a line and then doing a ReLU, what I'm basically doing is causing all of these decision boundaries like that. And so that's high probability, that's low probability. And so I'm learning these kind of like lines to kind of splice up the space. And so that's what every single layer is doing. And so you can see the more neurons I have, the more expressive it is. So because I have more decision boundaries to apply. And you can see each one of these is this kind of line that's going on here. And then the combination of these lines, can be much crazier the deeper and deeper you go. And so let's just, for example, just see this kind of what's going on here and let this one learn a little bit. And you see these lines start to form. These are the lines that it believes that to be a really good lines that's going to help solve this problem. You see it's not really working that well. That's because this is the hard one. Go back to the easy one for it to figure out these lines. That's no problem. And so, yeah. So, and then if you go back to the SGD here for a second, that learning rate is right there. So you can make this an aggressive learning rate or a really slow learning rate. Again, pros and cons. Truth be told, you're just going to try all the learning rates. The activation function, there's different ones. I recommend ReLU. It doesn't really matter. It's probably going to be fine if you use 10H as well. It's all fine. Regularization. And so the only thing to talk about on regularization is when you have these thetas, if you don't use this regularization term, which I'll explain in a second, then your gradients can explode. And that's really bad because then you get to very rocky training. And so let's see if I can make that happen. Make a really hard example and maybe give it a really high learning rate like that. And so you should see the deep learning model to have a lot of chatter. Maybe I can try it on a regular regression problem and see if that causes it. Maybe not. One more try, then I'll move on. There you go. That's exactly what we're trying to cause. So you see that? That's a lot of chatter. That's because I didn't have regularization. If I added regularization, it would make it a lot smoother training, and I can be in L2 regularization. And not really that much. Bring this down a little bit. Maybe this would be a little better. There you go. See? Now it's a much smoother training. So that's what we want to achieve. So what I want you to do is I want to go to this spiral one. Make it easy. Go on the low noise one, and then try your hardest to add a bunch of neurons and play with the learning rate, play with the regularization, and try to let it train and see if it learns. So I'll let you pause now, and we'll come back in a few seconds. All right, so we're back now. How'd you do? There's no right answer to this. So this is the alchemy of deep learning. The truth be told, there is no right answer in any architecture. There's just some things that work better, some things that work not so great. I found this one. If you were struggling to find anything, this one is a great one. And so you can see how complex this model actually ends up getting. So remember, every layer kind of ends up being this decision boundary. The combination of those layers, if you give it more input representation, you make it easier on the model, because a bunch of lines is never going to solve this thing. And so this is increasing your input data as a combination of your existing x1 and x2. So I can add in x1 squared, x2 squared into my model. That's going to make a more expressive model. The geometric combination of my model, of my inputs, the sign of my inputs, all those transformations will help me solve it. And then you can see the decision boundary that gets formed from that neuron. And then I added a bunch, and then you end up with this. And so this is about as good as one can hope for in this problem set, in this problem that we're trying to solve. And you can see how it generalizes, and you can see that the test loss gets very close to 0, which is great. That means that we're doing great. All right. Well, congratulations. You have trained your first deep learning artificial neural network. I hope this was enjoyable, and let me know if you have any questions. Thank you so much. See you in the next one.